Right. So, we now come to the last topic that I will discuss in this course, and the topic is self stabilization. So, what is self stabilization? As the name suggests, it is a mechanism by which a set of processes will reach certain stable states of the system, right. So, let us go through the definitions of what we mean by self stabilization, and then we will see how different algorithms can be developed to achieve self stabilization. So, first the definition of self stabilization. A system S is self stabilizing with respect to a predicate P if it satisfies the following two properties. First property is called the closure property, which says that if P is closed under the execution of S. Okay. What does that mean? Yes. That is, once P is established in S, it cannot be falsified, right. So, what does this mean? That S is the self stabilizing system. Okay. That means, once S reaches a state which satisfies P, it will forever remain in states which satisfy P. That is the meaning of this. Okay. Right. So, there is no edge, there is no transition from a stable state or a state which satisfies P to a state which does not satisfy P. Okay. The second property is convergence. Starting from an arbitrary global state, S is guaranteed to reach a global state satisfying P within a finite number of state transitions. Okay. So, the two together means the following thing, that you start from any state S0 which may not be satisfying the predicate P, but within a finite number of transitions you will reach some state Sk which satisfies P, and thereafter you will get trapped in a set of states, all of which satisfy P. Okay. That is what is the meaning of a self stabilizing system. So, it starts from any state, whichever state it starts from, it will converge to one of the states which satisfies P, and thereafter it will stay forever in the state which satisfies P. Okay. And what is P? P is some predicate defined over the state variables. Then there is another definition which is called stabilization, not self stabilization, but stabilization. Now, we define stabilization for system S with respect to two predicates P and Q over its set of global states. Predicate Q denotes a restricted start condition. S satisfies Q to P, read as Q stabilizes to P, if it satisfies the following two properties. First property is the same as before, P is closed under the execution of S, that is, once P is established in S, it cannot be falsified. The second property is, if S starts from any global states that satisfies Q, then S is guaranteed to reach a global state satisfying P within a finite number of state transitions, right. So, what is the difference between this and the previous definition? The difference is, right. So, it has to start from any global state that satisfies Q, this is the difference, right. and if you start from a state which satisfies q, then it is guaranteed to reach a global state satisfying p within a finite number of state transitions, and thereafter it is going to remain in state satisfying p, right. So, you might say that self stabilization is a special case of stabilization where the predicate q is true, right. If the predicate q is true, then stabilization actually is the same as self stabilization, right. Then there is a definition of randomized self stabilization. A system is said to be randomized self stabilizing system if and only if it is self stabilizing and the expected number of rounds to reach a correct state is bounded by some constant k, right. Now, see, previously we said that once it starts from a particular state, it will reach a state satisfying p within a finite number of transitions, right. Now, when we talk about randomized self stabilization, we only say that the expected number of steps is finite, okay, and constant. So, the expected number of steps to reach a state satisfying p is bounded by some constant k, right. Now, as you know from probability distributions that even though the mean is finite, it is not necessary that every value that the random variable takes has to be finite, right. So, but the probability that values which are arbitrarily large will take place is going to be lesser in most of the distributions that you see. So, it can be more or less centered around the mean, right. And as you go away from the mean, the probability of those values being taken decreases. That is there for most of the distributions, and of course, we have some distributions where this does not hold, right. So, when we talk about randomized self stabilization, it means that the actual number of steps to reach the stable state is a random variable, and the random variable follows certain distributions for which the mean is upper bounded by a constant k. That is what this means. Clear? Then we have probabilistic self stabilization. A system S is said to be probabilistically self stabilizing with respect to a predicate p if it satisfies the following two properties, that p is closed under the execution of S. This is same as before, but here there exists a function f from natural numbers to 0 1 satisfying limit k tending to infinity f k equal to 0, such that the probability of reaching a state satisfying p starting from any arbitrary global state within k state transitions is 1 minus f k. Now, how is this different from the previous one? In the previous one, we said that what did we say? We said that the mean of the distribution is upper bounded by k, right. What are we saying here? We are saying that we are giving you k and we are telling you that the probability that you will reach the goal, namely a state satisfying the predicate p within k transitions is 1 minus f k, right. So, we are fixing up k, the number of transitions to reach the goal, and we are saying that the probability that you will reach it by that number of steps is 1 minus f k.
Here also we can get an expectation.
Yes, it's see, probabilistic self stabilization and randomized self stabilizations are are semantically very close to each other, right. They almost have the same meaning, except that we are fixing up bounding two different things In the previous case we said that the mean of the distribution should be less than k, right. Here we are not saying that, we are saying that okay, you take a k and I tell you that the probability that it is going to reach a stable state within k steps is 1 minus f k. Okay.
This is just another way of putting it.
They are not equivalent definitions by the way, but they are very similar in to each other. The intent of both of them is similar. We want to have some kind of random bound on the number of states, number of transitions needed before you reach the stable state, right. Both of them are trying to give some bound on that, random bound. Okay. One is trying to put a bound on the mean, the other is trying to put a bound on the probability of reaching it by that number of steps. Okay. This is the difference. What are the issues in the designing of self-stabilization algorithms? After this slide we will start getting into individual problems where self-stabilization is needed, and then we will start looking at the algorithms. Now the things that we need to look at is the number of states in each of the individual units in a distributed system, okay, because the global state space of a algorithm is the product of the number of states in each of the processes, right. So the number of states in each of the individual units in a distributed systems, they sort of multiply with each other to give you the state space of the entire global system. Then there is we have to choose between a uniform and non-uniform algorithms. We will come to this later. We will look at central and distributed daemons. It may be a centralized self-stabilizing algorithm or it may be a completely distributed algorithm. Okay. This is a special case. We will not discuss this, that you can have algorithms for reducing the number of states in a token ring. We will see one or two examples of this. Then we will also, it will also depend on what is the shared memory model, whether it is shared, in what way it is shared, within how many processes is it shared. We will look at mutual exclusion algorithms which are self-stabilizing, and we also will look at the costs of self-stabilization. Okay. Now the notion of self-stabilizing algorithms originated with Dijkstras self-stabilizing token ring algorithm, and the problem there is as follows, that we have a distributed system consisting of a set of processes, right. Now we want to have a privilege which is shared between them. Privilege intuitively could be something like your ability to enter the critical section. Okay, so whichever process has the privilege can enter the critical section. Okay. Classically Dijkstra developed this algorithm with the mutual exclusion problem in mind, right. So initially more than one process may have the privilege, but then initially mutual exclusion will not be guaranteed. What we want is that the processes, they follow some protocol by virtue of which they reach a state where only one process has the privilege, okay, and thereafter in every state of the system at a time only one process will have the privilege, and we have to guarantee that there is no starvation, that is every process gets the privilege infinitely often, right, and that mutual exclusion is guaranteed, that at a time not more than one process will have the privilege. So is the problem clear? We start with a set of processes where more than one process may have the privilege, but then we want to converge to a state where only one process will have the privilege, and thereafter the privilege will be shared in such a way that everybody will have access to the privilege within a finite amount of time, and at a time only one process will have the privilege. Right. Let us look at the steps. A legitimate state must satisfy the following constraints. There must be at least one privilege in the system, right, which is equivalent to saying liveness or no deadlock. It should not be the case that deadlock means that nobody is able to enter, which means no one has the privilege, right. So, that should not happen. Every move from a legal state must again put the system into a legal state. Okay. So, that is the closure property, and during an infinite execution each machine should enjoy a privilege an infinite number of times. So, there should be no starvation, right. And given any two legal states, there is a series of moves that changes one legal state to the other, which is the reachability requirement. So, these are the requirements that are necessary for the problem. Dijkstra considered a legitimate or legal state as one in which exactly one machine enjoys the privilege, right. So, when in a state where exactly one machine has the privilege, that is considered to be a legal state. Okay. This requirement that only one state has the privilege is the predicate P that we had talked about when we defined self-stabilization. So, this corresponds to a form of mutual exclusion, because the privilege process is the only process that is allowed in its critical section, and once the process leaves the critical section it passes the privilege to one of its neighbors. So, let us look at the first solution for the first of Dijkstras solution. Dijkstra actually proposed 3 solutions, of which the first one is easy, the second one is very hard, the third one is harder still. Okay. So, we will first study the first solution, and for which it is intuitively easy to understand and the proof is also easy, and then we will see what are the drawbacks of that, and then we will see the second solution. Okay. We will not go into the third solution. So, here is the first solution. For any machine, we use the symbols S, L and R to denote its own state. There is a typo here. Its own state, then state of the left neighbor and the state of the right neighbor on the ring respectively. Okay. Now, there are 2 types of machines in this algorithm. One is called the exceptional machine, that is one particular machine which has a special status, right, not in terms of having more access to the critical section or anything like that. It is just one machine which executes a code which is different from that of the others. Right. So, the exceptional machine does this thing. So, these processes, they are arranged in a ring, right. So, that is why you have a left neighbor and a right neighbor in the ring. So, this exceptional machine checks that if the value of the left neighbor is the same as S, if it sees that it is the same as S, then it increases its state to S plus 1 mod k, where k is some constant greater than n. K is some constant which is greater than n, where n is the number of processes, right. What does the other machines do? The other machines check whether if L is not equal to S, then it sets S equal to L. Okay. Right. Now, the claim is that if you do this, if you execute this algorithm, then you will always reach a state where only one machine will have the privilege, will be able to execute, the other machines will not have the privilege. right? Yes. Any machine which can execute its code has the privilege, right? So, if the exceptional machine finds L equal to S, then the exceptional machine has the privilege. If any other machine finds L not equal to S, then that machine has the privilege, right? So, let us start with an example first, and then we will see more cases. So, let us start with a ring of this is the ring. Okay. Let us start with the initial values for these. Let us say k is 7, right. So, we start with let us say this being 3, 1, 2, 6, let us say 4. Okay. And let us say this is the exceptional machine, right. Now, initially you can see that let us look at the exceptional machine, which is its left neighbor, this one, right, and its left neighbor, does it have the same value as this? No. Then what do we have for the exceptional machine? Let me write it down here so that you can see everything in the same thing. Exceptional machine will do the following thing. If L equal to S, then S is S plus 1 mod k, that this is for the exceptional machine, right. So, what do the other ones do? The other ones check if L is not equal to S, then S equal to L. Okay. So, this one is for the exceptional. So, what will the exceptional machine do here? This is not equal to S, so it does not have the privilege, right. So, it is not going to do anything. Now, let us look at all of these other ones. For all of the other ones, L is not equal to S. So, all of them have the privilege, right, and they are all going to do what? They will copy the values of their neighbors. It will work for both cases. Okay. So, now let us see what will happen here, that this will update itself to, it will copy its left neighbor's value, right. So, this will become 6, right. What will this become? 2. What will this become? 1. What will this become? 3. Right. No, you can. So, this is one execution, right. Next, what will happen in the next round? This will become 2. This will become this, it will remain, right. Then what will happen? This will become 1, this will become, this will remain in 3, right. Next round this one will become, right. Now when this is the state, in the next round only exceptional machine has the privilege, no one else has, right. So we have reached a state where only one machine has the privilege, right. Now what is this going to do? Change it to 4, right. It will change it to 4. What will happen in the next round? Which machine has the privilege? 2 has the privilege, because in the next round only 2 will be able to execute, right. So this will become 4. What about the next round? Only 3 will have the privilege, it will become 4. In the next round only 4 will have the privilege, so it will become 4. The next round only 5 will have the privilege, this will become 4, right. Then what will happen? This will change to 5. Next round only this will have the privilege. Now you see, thereafter it is just going to, the privilege will just go around in this cycle, right. So initially they will all stabilize to a state where only one process has the privilege, and thereafter they are going to maintain that, right. So everyone will start copying their values of the left neighbors until you reach the exceptional machine, and then the exceptional machine will increment that value modulo k, and this is going to continue, right. Okay. Now this is a ring, algorithm for a ring. Once the privilege is, once you reach a state which has only one privilege, then it will only start going around the ring. So why don't you suggest an algorithm for doing it in a simpler way? No, you have to start with a system which is not stable, right. If you, how will you first of all start with a state which has only one token? This is a situation where the initial state can be any state, even a state which has multiple tokens, and you have to converge to a state where there is only one token and that is being passed around.
This algorithm always has the exceptional node as the first node to have the single privilege.
No. I mean, you are saying that it will always converge to that. Maybe, but the initial state of the system is one where multiple processes have the privilege. Right. So that's the challenge. The challenge is that you start with any arbitrary state of the system. That state of the system can have multiple privileges. In your terminology for a token ring, you may say that it starts with in a state where there can be multiple tokens in the system, and you want to reach a state where there is only one token left. Okay, not many tokens, not 0 tokens, exactly one token should remain, and then that token has to be shared properly among the processes. Stabilization is all about the initial part of the thing, given that you can start with any random situation.
But if the initial states, do they matter?
No, the initial states are not in your control. you cannot specify the initial state. The initial state, it will start in a random initial state. Let us say your algorithm has to guarantee that eventually within a finite number of transitions it will reach a valid state, and thereafter it will always remain in the valid state, right. In the context of mutual exclusion, validity means only one node can be in the critical section at the same time. Exactly one node should be in the critical section. It should not be that nobody has the privilege and that everybody is deadlocked. That should not be the case. And the fairness thing should be there, that there should not be starvation for any process. Right? That is the definition of validity for a mutual exclusion system. And this algorithm says that no matter in what state you start, you will eventually converge to valid states and stay there forever. Okay. If you are able to choose your initial state or force the initial state of the system, then you don't need stabilization, because then you are starting from a valid state, and all you need is an algorithm which does not do anything bad to take you from a valid state to an invalid state. Are you getting me? Now, do you remember some other algorithms which you have studied in the past where we did some kind of self-stabilization?
That once everyone has the majority has been decided once, it will remain a majority. Phase king.
No, you are saying Byzantine agreement? The Byzantine agreement is, I think a better example would be consensus, because when every process starts with some value and then they want to agree on some value, right. So, they sort of communicate between themselves and stabilize to a state of the system where all of them agree on the same value. Okay. And once they agree, then thereafter that agreement is kept. Right. So, you might say that that is one notion of stability. Right. Any other examples that you have seen? Election, where everybody starts with their version of the leader and then they stabilize to a single leader. Right. Anything else? What about routing algorithms? You remember? You can have changes in the network, and then the new node which comes up, that starts broadcasting its tables to the other nodes, and everybody should eventually again settle down to the shortest path routes, right. So, there will be a point of time where your routing table even may have cycles, right, and then finally they will again stabilize into a system where you have routing through the shortest paths again, right. So, these are practical examples of where you do not make any assumption about the initial state of the system. Initial state of the system can be arbitrary, but the nodes, they coordinate with each other to arrive at agreements or stable results on some global properties of the system. Like shortest path between two nodes is a global property, it is not local, right, and that is what you stabilize into, that is what you settle into.
Agreeing to enter a critical section, that would mean what? Would that also mean a number of mutual exclusion also, sir? Would that also be coming apart?
No, there provided, you see there it is very clear, you start with a system in a system where nobody has the privilege, right. That is the assumption that we did in all the mutual exclusion algorithms. Your start state is one in which the property that only one process is in the critical section is valid, and then the algorithm maintains that thing. Okay, but you do not start in a state where multiple processes are in the critical section.
You can start from a state where no process is in the critical section.
You can start from a situation where no process is in the critical section, but there also implicit in the algorithm is that somebody has the privilege, right, and the privilege is gained by sending out request messages to everybody and getting the replies back. Then you gain the privilege, right. On the other hand, the types of algorithms that we are talking about here is in the initial state certain property may not be satisfied, like the initial routing table values may not actually reflect the shortest path distances, right, but once the algorithm stabilizes then they do. Okay. So, they are starting from a state where your property, the property that your routing path distances should be the shortest path distances, does not hold, but then after the computation the routing algorithm runs, and it guarantees that eventually you will reach a state where at each node the routing table satisfies that property. And thereafter, unless another perturbation takes place, that is some node goes down or something like that, they are going to maintain that. So, that is why that is an instance of a self-stabilizing algorithm. Okay. We will quickly look at the description of the second solution of Dijkstras token ring algorithm, and with that we will call it a day, but I want you to ponder on this algorithm, and if any of you, without looking up the proof of it, if you can understand the algorithm and give me an intuitive explanation, then I will be very happy about that. Then I will know that you have really spent some time in trying to understand how that algorithm works, right. This is the algorithm. Here we have three types of machines. See, in the previous solution we had two machines, one was the special exceptional one and we had the rest of them. Now, here we have two special types of machine, one is called the top machine and the other is called the bottom machine, and the remaining are the rest of the machines. Okay. Now, one thing that we must note is that in the previous case, what is the number of states that each machine can go through? K, because it is going to start from 0, 1, 2, 3, 4 up to, right. So, it has k different states. So, 0 through k minus 1, those are the states it can take, but that can be a lot of states because k is an upper bound on n and you can have quite a large number of machines. So, Dijkstra's second solution uses only 3 state machines. So, every machine has only 3 states, 0, 1 and 2. Okay. That is why the second algorithm was proposed, that you do not need to have k states in every machine, you can do with only 3 states in every machine and still you will be able to satisfy all those requirements. Now, this is what the bottom machine does. If s plus 1 mod 3, now mod 3 because we have only 3 states, if s plus 1 mod 3 is equal to r, then you set s equal to s minus 1 mod 3, right. The top machine does the following thing: if L equal to R, if the left and the right have the same value and L plus 1 mod 3 is not equal to S, then we set S to be equal to L plus 1 mod 3. And this is what the other machines do. If S plus 1 mod 3 is equal to L, then S equal to L, and if S plus 1 mod 3 equal to R, then S equal to R. Right?
So top
make these slides available, and also I will make some literature available on that. Both, in fact, the literature most probably is already there in there's okay, so it's already been made available. So you go through that, but that literature is not sufficient to understand why this is going to stabilize, right? That's what I want you to think about. Okay, so with that challenge we reach the end of this lecture.